Hello and welcome to MyScience Tutorials. In today's video, we are going to be talking about heat energy, that is, introduction to heat capacity and latent heat capacity. Before we begin, if you are new to MyScience Tutorials, kindly consider subscribing and pressing that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's go ahead. So when energy is introduced into a body or a substance, the kinetic energy or the potential energy of the substance may increase or change. Now, depending on which of these two energies are changed, there may be change in temperature or there may be a change in the state of the matter. Now, for instance, if we have a change in the kinetic energy of the body, it results in a change in temperature of that particular body, but not the change in the physical state of the body. But any change in potential energy is manifested by the change in the physical state of the body. So let's look at these two examples over here. So like I said, an increase or change in kinetic energy results in a change in temperature. So you can see that this metal bar over here has been subjected to heat, and with time you can realize that the tip of the metal bar over here is really hot, and so we know that the temperature over here of the metal bar without the heat will be very low, and then the temperature over here will be high because it has been subjected to heat. Now, when there is a change in the potential energy of the body, we can see that there is a change in the state of matter. So we can see that we have an ice over here, which is what, solid. But then after some time, and there is, let's say it has been removed from the refrigerator and it has been placed in an open environment where the temperature difference is high, you can see that the solid or the ice begins to melt from the solid state to the liquid state. Okay, so we have ice water over here, and then with time or over time, you can see that the entire ice will melt and it will become what, water. So there's a change in state occurring over here, and that is as a result of what, a change in the potential energy, and that is manifested by what, the change in the state of matter. All right, so we want to look at what heat capacity is. So heat capacity denoted by capital C. Now, the heat capacity of a body is defined as the amount of heat energy needed to raise the temperature of the body by 1 Kelvin or 1 degree Celsius. So if we have any body, let's say a solid or a liquid, just the amount of heat that you apply to it before you are able to raise the temperature of that particular substance or matter by 1 Kelvin or 1 degree Celsius is what we termed as the heat capacity. So heat capacity is given by, mathematically, it is given by capital C, which is equal to Q over what, delta. Now, delta or theta over here is the temperature change, which is what, the 1 Kelvin that we are talking about, and then the Q is the heat supplied. So the ratio of the heat supplied over the change in temperature gives us our what, our heat capacity. It has the unit of what, joules per Kelvin or joules per degrees Celsius. Now we have something else we call the specific heat capacity, denoted by what, small c. Now the specific heat capacity of a body is defined as that amount of heat energy needed to raise the temperature of what, 1 kilogram of the body by 1 Kelvin or 1 degree Celsius. So we can see that the difference between the heat capacity and then the specific heat capacity is that with the heat capacity, you are just changing the temperature of the body by what, 1 Kelvin or 1 degree Celsius. But when you know the particular mass the body that you are changing, and it is what, 1 kilogram. So if you're changing the temperature of 1 kilogram of a body, it means you know the mass that you are dealing with, so it becomes what, specific heat capacity of that particular body. So simply put, specific heat capacity is the heat capacity per unit mass of a substance. So we can see that from this definition over here, that is the heat capacity per unit mass of a body or a substance, we can see that the specific heat capacity, which is the small c over here, is equal to or is equivalent to what, the heat capacity, which is the capital C we have over here, on what, the mass of the body. Okay, but from heat capacity, we know that heat capacity is the heat on the change in temperature. So if we do the substitution of what heat capacity into the specific heat capacity over here, that is, we substitute this in place of the C we have over here, we get what our specific heat capacity, which is small c, to be equal to what our heat energy on the product of what mass and then change in temperature, okay, as given over here. Now if we make the heat energy or the heat supply the subject, we get what Q to be equal to what mc delta or theta, okay, where our Q is the heat. This is the quantity of heat. So our Q is the quantity of heat supplied, our m is the mass of the substance, our C is the specific heat capacity, and our delta or theta is the change in temperature. Now this formula is very, very important when we are dealing or we are solving problems related to what heat energy. So the heat energy of a body is equivalent to the product of the mass, the specific heat capacity, and then the change in temperature of that particular body. Alright, so we want to look at what sensible heat and latent heat are. Now sensible heat, this is the heat that produces a change in temperature of a substance without a change in state. So we can see that the example that I gave over here, we have a solid metal bar, so it is solid, and then at the end we still have what a solid over here. Okay, the only difference between these two metal bars is that the tip over here has been subjected to heat, and then over here it is what red hot. That is what the temperature between the tip over here and then the temperature over here are not the same. So we have a change in temperature, but we do not have a change in the state of the matter. And when that occurs, we classify that type of heat as what sensible heat. Now, in the case where the heat applied to that particular substance is able to transform the substance, okay, from one state to another, then it becomes what latent heat. So latent heat, this is the quantity of heat absorbed or released when a substance changes its physical state at a constant what temperature. So we can have an example. A good example is the usage of ice. So we have ice freshly removed from the deep freezer. So we have the ice, it is in a solid state, but with time it begins to melt, okay, and then when it's melting, the temperature over there is still at what 0 degrees Celsius, where we can observe what a change in the physical state of the matter, that is from what, from solid to liquid over here. Okay, another example is when we have a bowl of water and we subject it to heat. So when we are heating, we get to realize that when the temperature of the water reaches what 100 degrees Celsius, the water begins to boil. So at that temperature where the water begins to boil, we can see that the water is being converted from what, the liquid state to the gaseous phase, but the temperature over there is still 100 degrees Celsius, but we are having a change in the state of matter, and that particular heat that is causing the change in the state or the physical state of the matter is what we are calling what, the latent heat. All right, so now that we know what sensible heat is and latent heat is, let's go into the various types of latent heat that we have. So we have specific latent heat of what, vaporization. Now this is the quantity of heat required to change 1 kilogram of a liquid at its boiling point to vapor at the same temperature. So like I said earlier on, if you're able to change a liquid at its boiling point to vapor or into the gaseous phase at the same temperature, that particular type of heat energy you're applying is what we call the latent heat of what, vaporization. So the latent heat of vaporization, that is what LV, is given mathematically as the heat energy supplied on the mass of the body, okay, and then the unit is what, joules per kilogram. Okay, so to simply put, if you have a water and you boil it and it's at 100 degrees Celsius and it has changed from liquid to gaseous, and you want to know the amount of heat energy at that particular point, all you need to do is what, is to multiply the mass of the water that you are heating by the latent heat of vaporization of water, and you can get your amount of heat at that particular what, temperature. All right, so the specific latent heat of fusion is the second one that we want to look at. So this is the quantity of heat energy required to change 1 kilogram of a substance at its melting point to a liquid without a change in temperature. So what we mean by this is, if you are able to change a solid substance to a liquid or a liquid substance to a solid, okay, that particular type of heat is what we are calling the latent heat of fusion. Okay, you can see that there is a change in the state of matter, but the temperature is still the same. So a good example is when an ice being brought out of a deep freezer, and then with time it is melting from the solid to the liquid state. That type of heat energy is what we call, or the transformation occurring at that point is what we call the heat of fusion. Or if we subject a metal bar to a high amount of heat to the extent that the metal begins to melt, okay, into a hot magma or a liquid, a molten state, that is also what the type of heat applied over there is what heat of fusion. Now the heat of fusion, okay, that is we are melting solid to liquid or liquid to solid, is given to us by also the heat energy on the mass of that particular substance or that particular solid or liquid. So the heat energy, if you want to know the heat energy, and then you have a transformation that is from solid to liquid or liquid to solid, you multiply your mass by your latent heat of fusion to get the heat energy involved in that particular type of what changing state that is occurring. And if you want to know the heat energy that is involved in changing a liquid to a gaseous phase, that particular heat energy can be calculated using the formula of what mass, or the product of what mass by the latent heat of vaporization. So now that we are done with looking at what sensible heat is, latent heat is, and what heat energy is, let's try to look at some few examples so that you can know how to use the latent heat of fusion, latent heat of vaporization in solving practical examples. So the first one we want to look at is, we are to calculate the heat energy needed to convert a 2 kilogram of ice at negative 12 degrees Celsius to steam at 100 degrees Celsius. So we are being given the specific heat capacity of water to be 4,200 joules per kilogram per Kelvin, then the specific heat capacity of ice to be 2,100 joules per kilogram per Kelvin, the latent heat of fusion of ice to be what, 336,000 joules per kilogram per Kelvin, and then our latent heat of vaporization to be what, 2,260,000 joules per kilogram per Kelvin. So let's look at the solution for this example. So let's write down solution. Alright, so let's analyze the question. So we have to calculate the heat energy needed to convert what? A mass of what? 2 kilogram of ice. So we have the mass is what? 2 kilogram of ice at what? Negative 12 degrees Celsius to steam at what? 100 degrees Celsius. Now, when it comes to this, there are a lot of transformations that are occurring over here, because we are looking at an ice being converted into a liquid first before we are boiling the liquid, or we are heating the liquid into what? The steam or the gaseous state. So there are 3 transformations that are occurring over here, and we need to look at that. I said 3. There are 4 transformations. The first one that we need to take note of is what? We need to change the temperature of the ice from negative 12 degrees Celsius to 0 degrees Celsius. So we change the temperature of ice from what? From negative 12 degrees Celsius to 0 degrees Celsius. And then there will be a heat energy needed to do this conversion. Now the second one is what? The change in state, because we need to change the ice, okay, from solid at what? 0 degrees Celsius to liquid, which is water, at what? 0 degrees Celsius. So we are converting the ice from what? Solid to liquid at the same temperature, but then there is a change in what? State of matter. Now the third one is what? We need to boil the water, or subject the water that we now have after the ice has melted. We have to subject it to heat. So we boil the water, okay, from boil from what 0 degrees Celsius to what 100 degrees Celsius. Okay, now once we boil the water to 100 degrees Celsius, we can see that the water will begin to what change state from what the liquid state to the vapor state. So we are looking at what the conversion of what water, okay, at what 100 degrees Celsius to what vapor at the same temperature, all right. So sorry about my ugly handwriting. So let's look at the energies involved in the first case. So the first case, we need to convert the ice from negative 12 degrees Celsius to 0 degrees Celsius. Okay, so the amount of heat energy required in this particular case is equal to the product of mass multiplied by the mass of ice, okay, multiplied by the specific heat capacity of ice, multiplied by what the change in temperature. All right, so the heat energy over here, let me use that as Q1. The mass of the ice we are given is what, 2. The specific heat capacity of ice is being given to us as 2100 joules per kilogram per Kelvin. And then the temperature change over here is from what? We know in terms of numbers, we know 0 is bigger than negative 12. So we have the higher temperature, which is 0, then minus then the negative 12 that we have over here. So our heat energy becomes what? 2 multiplied by 2100 multiplied by this becomes positive, so we have 12. So it means the heat energy needed to convert the ice from 12 degrees Celsius to 0 degrees Celsius is the product of 2 multiplied by 2100 by 12, and that will give us what? A total sum of heat energy of 50,400 joules. Okay, so this is for the first aspect of the calculation. Now the second aspect of the calculation is what? We have to convert the ice, okay, from the solid state at what, 0 degrees Celsius to a liquid state at the same, okay, temperature. So we can see that we are converting from what? Solid to liquid. Okay, solid to liquid. So it means we are dealing with what? Latent heat of fusion. Okay, latent heat of fusion. So our second heat energy, latent heat of fusion. So if we have a change in state, and we know that that change in state involves the latent heat of fusion, all we need to do is multiply the mass by the latent heat of fusion, and then we get the heat energy in that process. So the mass that we have, okay, is what? 2, then multiplied by the latent heat of fusion of ice is being given to us as what? 33,336,000. So if we do the multiplication, we are going to get 672,000 joules. Okay, so this is the heat energy needed to convert the ice at what? Solid state to the liquid state at the same temperature of what? 0 degrees Celsius. Now let's look at the third heat that we need. So we have to convert now we have water, so we have to boil the water from 0 degrees Celsius to 100 degrees Celsius. So the heat energy involved in that process is what? The mass of water multiplied by the specific heat capacity of water multiplied by what? The change in temperature. So the mass of water is still the mass of ice, so we are assuming no matter has been lost during the conversion. So the mass is what? 2 multiplied by the specific heat capacity of water is 4,200 joules. Then multiplied by the change in temperature over here is, we are converting from what? 0 to 100. So the change in temperature is what? 100 minus 0, which is still 100. So if we do the multiplication over here, we are going to get 840,000 joules as our energy required for this particular third step. So let's look at our fourth energy involved in this particular example. So the fourth one is we are converting water at 100 degrees Celsius to vapor at the same temperature. Okay, so we are converting from what? Liquid to what? To the vapor state, and that is what? Latent heat of what? Vaporization. Now from what I said earlier on, the latent heat of vaporization, if you want to know the amount of heat involved, is just the product of the mass of the substance multiplied by the latent heat of vaporization. So it means we multiply the mass of 2 by the latent heat of vaporization, which is 2,260,000. Okay, and so the heat energy in this process, that is converting the water from 100 degrees Celsius to vapor at 100 degrees Celsius, becomes what? We have 4,520,000 joules. All right, so now that we've calculated all our energies needed for the conversion, let's sum all our energies to get our total energy needed to convert the ice from negative 12 degrees Celsius to what? 100 degrees Celsius, that is vapor at 100 degrees Celsius. So our final or our total energy is the sum of what? All the individual energies needed for the 4 processes. Okay, so we have the sum of what? 5,400 plus 672,000 plus 840,000 plus 4,520,000. So our total heat, let me use blue for that. So our total heat energy needed for this conversion is what? 6,082,400 joules of energy. So this is the amount of energy we need to convert a 2 kilogram of ice at what? Negative 12 degrees Celsius to what? Steam at what? 100 degrees Celsius. All right, let's look at a new example. Example number 2. Water of mass 2 kilogram at a temperature of what? 30 degrees Celsius is heated by what? 5 kilowatt core. Calculate the time taken by the water to boil. Specific heat capacity of water is being given to us as 4,200 joules per kilogram per Kelvin. So let's go ahead and look at the parameters that we have in this particular example. So we have a water of mass 2 kilograms. So the mass is what? 2 kilogram at a temperature. So the initial temperature, I will use this, is what? 30 degrees Celsius. It's being heated by what? 5 kilowatt of core. And you know the unit, the kilowatt means is power. So the power of the heating mantle or whatever is used to heat the water is what? 5 kilowatt. All right. So we have to calculate the time. So we have time unknown. The time taken by the water to boil. So by water boiling, it means the final temperature is what? 100 degrees Celsius. So we are being given the specific heat capacity of water to be what? 4,200 joules per kilogram per Kelvin. All right. So let's analyze the question. Now, first of all, we need to know the heat energy that that is being supplied to the water to do the conversion, that is to move from 30 degrees Celsius to 100 degrees Celsius. So we need to calculate that heat. Now, after we find that heat, we can use that heat energy to find the time taken, okay, to for the water to boil. That is because if you look at power, okay, is equal to what? Heat energy divided by time. Okay, this is time. Okay, so that is heat energy, heat on time. So this is the power. So it means we need to first find the heat energy supplied. Okay, so after we find the heat, we can now easily find the time during using just some basic mathematics and substitution. So let's look at the heat energy. So our heat energy is equal to what? The mass of water, specific heat capacity of water, multiplied by what? The change in temperature. So our heat energy is what? The mass of the water is what? 2, multiplied by the specific heat capacity of water is 4,200, multiplied by the change in temperature over here is 100 minus 30, and that will give me what? 2 multiplied by 4200 multiplied by 70. Okay, and then this will give me a value, or an energy value of what? 588,000 joules. So this is my heat energy when you use a 5 kilowatt coil to boil water at what? 30 degrees Celsius to 100 degrees Celsius. So now that we have the heat energy, let's do the substitution and find the time taken for the water to boil. So from here, if we make time the subject over here, our time will now be equal to what? The heat energy, that is heat energy, the ratio of what? Heat energy on the power of the coil. So the time is now, the heat energy is what? 588,000 on the power is 5 kilowatts, so it's 5 times 10 raised to the power what? 3 watts. So if you do the computation, you get to realize that you are going to get a time of what? 117.6 seconds. So this is the time it took the core of 5 kilowatts core to boil 2 kilograms of water from what? 30 degrees Celsius to 100 degrees Celsius. Now let's look at one final example and then we end this beautiful tutorial. So example number 3. We are to calculate the quantity of heat needed to melt 4 kilograms of ice at 0 degrees Celsius and to raise the temperature of water formed to 50 degrees Celsius. So let's have a look at the parameters that we have. So we are to calculate the quantity of heat needed to melt 4 kilograms of ice. So the mass of ice is what? 4 kilograms. Okay, so we are to melt it at 0 degrees Celsius and to raise the temperature to 50. Now let's look at the changes that are occurring over here. First of all, the ice is at 0 degrees Celsius, so we need to convert ice at what? 0 degrees Celsius to water, okay, at what? 0 degrees Celsius. And this transformation is what? Latent heat of what? That is from ice to what? Water. So it's latent heat of fusion. Okay, so latent heat of fusion is being applied in the first case. So after that, we need to convert the water, okay, water at what? 0 degrees Celsius now to 50 degrees Celsius. Okay, and this is our normal calculation. So these are the two transformations that are going to take place. Okay, so let's look at the heat energy involved in the first process. So the heat energy involved in the first process is, this is latent heat of what? Fusion. That is, we are changing from solid to liquid. So that is what the product of the mass by the latent heat of fusion of ice. So the mass of the ice is 4 kilograms multiplied by the latent heat of fusion of ice is what? 336,000 joules per kilogram per Kelvin. So if we do the multiplication, we are going to get 1,344,000 joules as the first energy required to convert the ice at 0 degrees Celsius to water at the same temperature, that is 0 degrees Celsius. Now the second amount of heat that is needed to convert water from 0 degrees Celsius to 50 degrees Celsius is just the normal way of calculating the heat energy by a substance. So that is going to be the product of the mass by the specific heat capacity of water by the change in what? Temperature. Okay, so the mass we are assuming is still 4 multiplied by the 4,200, that is the specific heat capacity of water, 4,200, and multiplied by what? The change in temperature. Now the change in temperature in this example is going to be 50 minus 0. Okay, so we have 4 multiplied by 4,200 multiplied by 50, and that is going to give me a heat energy of what? 840,000 joules. Alright, so now that I have the two energies needed to convert the ice, or to melt the ice from 0 degrees Celsius and raise the temperature of the water formed to 50 degrees Celsius, all I need to get a total energy is just to add the first energy with the second energy. So I have the sum of what? 1,344,000 and 840,000. So let me quickly do that. So I'm adding 1,344,000 by 840,000. All right, so that is going to give me a total energy of what? 2,184,000 joules. So the total energy needed for this conversion, that is to convert the ice or to melt the ice at 0 degrees Celsius and raise the temperature of the water formed to 50 degrees Celsius, is 2,184,000 joules of energy. So thank you so much for watching. I hope you love this tutorial, and watch out for the subsequent tutorials on heat energy. We love you, and then stay safe and blessed. Bye bye.